Here we have a ramp, and we have a piano that's being pushed up that ramp. Piano has a mass of 3,000 kilograms. We are applying a force of 1,600 newtons. The ramp has an inclination of 20 degrees. And we're saying that there's no friction. Now, if this were really a piano, it would be on wheels. And anything that's traveling on wheels is indeed going to have very low friction indeed. So that's not an unreasonable statement or assumption to make. Let's draw the free body diagram. There is going to be weight pointed down. The normal force is always pointed at right angles to the ramp, something like this. And there's the applied force of our hero who is pushing it up the ramp. Now, let us draw in the axes. In any ramp problem except for a banked curve, you always draw the y-axis to be in line with the normal force and the x-axis to be in line with the applied force. Now, let's examine this vertical dashed line that I'm drawing. If this had been a flat surface, the normal force would have been aligned with this vertical line. But because we're on an incline, the normal force has gone 20 degrees away from that incline, which means that the angle between the weight force and the y-axis must also be 20 degrees. The weight force is the only force that is not aligned with one of the axes. So that means that is the one that we are going to have to break into its components. So the component which is on this adjacent side, this is the side that's adjacent to the 20-degree angle, is going to become weight cos 20. And the one that's on the opposite side will be weight sine 20. We have now completely broken down this weight vector, and we are ready to examine what is taking place in terms of the acceleration of this block. Now, the block is not accelerating in the y direction. It is not collapsing into the ramp, and it's not levitating from the ramp. So there's no real reason for us to calculate the y direction. We can safely ignore it. But in the x direction, we have an applied force, 1,600 newtons, and we have weight sine 20 in the opposite direction. So that means that in the y direction, the total force is going to be the applied force minus the force of weight sine 20 degrees. But total force is also equal to mass times acceleration. By the way, I don't know why I wrote y here. This is supposed to be x. So, applied force minus weight sine 20 degrees is equal to mass times acceleration. Now, let's solve for the weight. Weight is equal to mass times gravity, which is equal to mass, it was a 300 kilogram piano, times gravity, which is 9.81. That's going to work out to 2,943 newtons. So plugging that and all of the other known quantities in here, the applied force was 1,600 minus the weight was 2943 sine 20 degrees for the x component is equal to a mass, 300, times the acceleration. So the acceleration becomes the only thing we don't know. 1,600 minus 2943 sine 20 degrees gives us 593.43. Now, if we take that and we divide that by the mass, we get 1.98. The acceleration is equal to 1.98 meters per second squared, and that would be an acceleration in the I direction. So to recap how we got from this step to this last one, this entire left side becomes 593, which is equal to 300 times the acceleration. Then we just divided both sides by 300 to get an acceleration of 1.98. So that is the acceleration of the piano up the ramp. In this question, we have a snowboarder who is traveling up a ski slope. Something like that. Now, we were told that our character is traveling, first of all, on snow, and if we were to look in our book, we would find the force of kinetic friction, since this is a problem with friction, is going to be 0.1. We're also told that the angle of the slope is 5 degrees, but we were never told how heavy our snowboarder was. So that means that that's not going to be relevant to finding the acceleration of the snowboarder. It also means we can pick whatever mass we want and we'll get the correct acceleration. So let's draw the free body diagram. There is weight pointed down. The normal force is always going to be at right angles to the surface. And the friction force is always going to point down the ramp. Or more correctly, the friction force is going to point opposite the direction of motion. Since our hero is moving up the ramp, the friction force points down the ramp. Those are all of the forces. So now let's draw the axes. Here's the origin at the hero who is traveling up the ramp. In a ramp question, the y-axis is almost always put in line with the normal force, and the x-axis is almost always put at right angles to that. Or it has to be put at right angles to that. 90 degrees. I'm going to set my positive x direction to be down the slope, because that way the components that are important in the x direction will both be positive. Now I see that the normal force is in line with the y direction, and the friction force is in line with the x direction. That just leaves the weight force. So we need to break the weight force, which is at an oblique angle, into its two coordinates, into its x coordinate, its x component, and its y component. Now, if this had not been a ramp, if this had been a flat surface, the normal force would have pointed straight up. Something like this. But because the slope is tilted by 5 degrees, the normal force is 5 degrees away from that vertical line that it would have been on, which means that this angle over here is also 5 degrees. That's the angle between the weight force and the y-axis. So, the weight force has one component which is on the opposite side of this angle. So this now becomes weight sine 5 degrees, and this side, which is adjacent to the angle, which becomes weight cos 5 degrees. Now we have broken our weight force into its components, and we are ready to analyze the forces in both directions. Now, because this has a kinetic friction, we have to analyze what's happening in the y direction first, because we don't yet know what the normal force is, and the kinetic friction, of course, depends on the normal force. So in the y direction, the total force is equal to normal plus negative weight cos 5 degrees, but total force is also equal to mass times acceleration. So normal force plus negative weight cos 5 degrees equals mass times acceleration. Now let's take the weight. Let's find out what the weight is. The weight is equal to mass times gravity, but we were never told what the mass of our snowboarder is. So that means that is irrelevant to the question if you were not told that. It also means you can pick whatever value you want for mass. Let's pretend that this is actually a snowboarding gnome, and the gnome has a mass of 1 kilogram. The weight of the gnome would therefore become 9.81 newtons. So let's plug in what we know. Normal force minus 9.81 cos 5 degrees is equal to mass, 1, times the acceleration in the y direction. Our snowboarder is not collapsing into the ramp, and he's not levitating from the ramp, which means that the acceleration in the y direction is 0. This entire right side goes away. So 9.81 cos 5 gives us 9.77. The normal force, if you were to move this to the other side, you would end up with normal force equals 9.81 cos 5 degrees, which is 9.77 newtons. And this would be pointed in the j hat direction. So that's the normal force, which is half of what we need for this question. In the x direction, the total force is going to be given by two forces, or two components. One is the force of kinetic friction, which is pointed in positive x, and the other is weight sine 5 degrees, also pointed in positive x. But total force is also equal to mass times acceleration. So we are now going to find out what the acceleration of the snowboarder is, and since I set downwards, down the ramp as being positive, we're going to find out what that positive acceleration is because our snowboarder is initially moving in the negative direction. Regardless, we now have the kinetic friction plus weight sine 5 degrees is equal to mass times acceleration. So we already know the weight. We said that the weight of our character was going to be 9.81 newtons. And the reason why we said that was because we were never given a mass. So we could just assume what the weight was what the mass was. We decided on 1 kilogram. And if our character has a mass of 1 kilogram, then the weight would be 9.81. So that just leaves the kinetic friction. Kinetic friction is equal to mu times the normal force, which is equal to 0.1 times a normal force of 9.77. 0.1 times 9.77 is going to give us 0.977. So that is the size of the kinetic friction. So we now have 0.977 plus 9.81 times the sine of 5 degrees is equal to the mass of our snowboarder, which we said was 1 kilogram, times the acceleration. So 0.977 times 9.81 sine 5 degrees gives us 0.835. Sorry, yes, 0.835. So that means that when all of the dust clears, we end up with an acceleration of 0.835 meters per second squared. And this would be pointed down the ramp, which we said was the positive direction for x. So that is the acceleration of our snowboarder down the ramp. Here we have a 20 kilogram object which is sliding down a ramp. 20 kilograms. the force of kinetic friction is the coefficient of kinetic friction, I should say, is 0.03, and the angle of the ramp is 30 degrees. So now, let's draw a free body diagram. This object is going to feel the weight force pointed down. The normal force is going to be at 90 degrees to the ramp. And a friction force is going to point opposite the direction of motion. So since this is sliding down the ramp, the friction force must point up the ramp. Like that. Now, let us draw the origin and axes. So here's the origin on the object, as always. So that's the y direction. That's the x direction. Now, if this object had been on a flat surface, a level surface, then the normal force would have pointed straight upwards. But because this is a tilted surface at an angle of 30 degrees, the normal force points 30 degrees away from the vertical, which means that this angle here between the weight force and the y-axis must also be 30 degrees. So now normal force is along one axis, the kinetic friction is along another axis. Let us now draw the components of the weight force. So the opposite side, or this side over here, which is parallel to the x-axis, is now the opposite side of this triangle. So this is going to be given by weight sine of 30 degrees. And this is the adjacent side, which is given by weight cos of 30 degrees. All right, now all this said, let us work out what is happening in the y direction. We have to solve for the y direction first, because even though there is no motion in the y direction, it isn't collapsing or levitating from the ramp, this y direction gives us the normal force, and the normal force is required to find the friction. So in the y direction, the total force is equal to normal plus negative weight cos 30 degrees. But total force is also equal to mass times acceleration. Therefore, normal minus weight cos 30 equals mass times acceleration. The weight of this object is given as mg, where mass is 20, g is 9.81. So when you work that out, that's going to come to 196.2 newtons. So normal force minus 196.2 cos 30 degrees is equal to the mass, 20, times the acceleration. But in the y direction, the acceleration, as we said a moment ago, is 0. So this entire right side cancels out. Now, 196.2 cos 30 is 169.9. So moving this to the other side, we end up with a normal force of 169.9 newtons. And this would be pointed in the j hat direction. Now, in the x direction, there are two forces, the sine component of weight and kinetic friction. So the total force is weight sine 30 minus the force of kinetic friction. But again, total force is equal to mass times acceleration. So putting everything together, we get weight sine 30 minus kinetic friction equals mass times acceleration. Now, in this, we do not yet know what the kinetic friction is, so let's solve for that. Kinetic friction is equal to mu k multiplied by the normal force. So, since we know that mu k is 0.03 times a normal force of 169.9, as we worked out before, that gives us a kinetic friction of 5.097. Now, the weight we already calculated as 196.2. Sine 30 degrees minus the friction of 5.097 is equal to the mass, 20, times the acceleration. So, 196.2 times the sine of 30 degrees minus 5.097 gives us 93 newtons, which is equal to 20 times the acceleration. So the acceleration is going to be 93 divided by 20, which is 4.65. And since this is sliding in the positive x direction, I should say 4.65 I hat meters per second squared. The last part of this question was to figure out what the velocity of this block was going to be once it reaches the end of this ramp. Now, we were told that the length of the ramp was 2 meters. So that means that since we're looking for a velocity, that's no longer a force question. That is a kinematics question. Because there is very few places where velocities are directly used in forces. They're most prevalent in kinematics. So let's draw one of our kinematics tables. Delta x, v initial, v final, acceleration, and time. The acceleration we just figured out was 4.65 I hat. The final velocity is what we're looking for. The initial velocity was 0, and the displacement of the box is 2 meters. There's only one equation that weaves together all 4 of these quantities, and that's toolbox equation 4. V final squared minus V initial squared equals 2 times acceleration times delta x. So V final squared minus V initial is 0 squared is equal to 2 times 4.65 times x, which was 2 meters. So 2 times 4.65 times 2 gives us 18.6. So we now have, this cancels and we have V final equals 18.6, or rather V final squared equals 18.6. So the square root of that is 4.31. V final is 4.31 meters per second, and this is in the I hat direction. In this question, we were given a pulley which was attached to the edge of a ramp, something like this. Now we were told that the dangling mass has a mass of 4, and the mass on this surface has a mass of 2. there is no friction anywhere, mercifully for us. So we need to find out what the acceleration of this system is on the understanding that this angle here is 40 degrees. In a pulley question, you have to solve for both of the free body diagrams for these two moving objects. Let's start with the 4 kilogram one. The 4 kilogram object is going to have a weight force pointing down and a tension force pointing up. By contrast, the 2 kilogram object is going to have the weight force pointing down, a tension force that points in the direction of the rope, and a normal force that points at 90 degrees to the surface of this ramp, so somewhere off in this direction. Now let's set the origin and the axes. For the 4 kilogram object, I'm going to set my y-axis to point downwards, with the origin obviously being at the spot, as it always is in any force puzzle. For the 2 kilogram object, I will set my y-axis to be in line with the normal force as occurs in any ramp, and the x-axis to be in line with the tension force. And to keep things simple, I'm going to put my positive x direction as being over here. So this direction up the ramp is going to be positive x. And the reason for that is because if I set it like this, then both the 2 kilogram and the 4 kilogram object will have positive accelerations. Now, if we had been on a flat surface, the normal force would point straight upwards. But since we're on a tilted 40-degree incline, the normal force is 40 degrees away from the vertical line that I've just drawn here, which means that the weight force is also 40 degrees away from this y-axis. Now, let us break the weight into the components, because normal and tension are already along the axes. So this side, the one which is on the y-axis, is the adjacent side to this angle. So this becomes weight cos 40 degrees. Whereas this side is opposite the angle, so it will become weight sine 40 degrees. All right. Now, because there's no friction in this question, we don't need to solve for what's happening in the y direction for the 2 kilogram object. We only need to bother with what's happening in the x direction, and we'll compare that to what's happening in the y direction for the 4 kilogram object. Actually, let's start with the 4 kilogram object. That was probably going to be a little bit easier to analyze. So for the 4 kilogram object, in the y direction, the total force is going to be given by the weight force, which is pointed downwards, minus the tension force, which is pointed in the negative direction. But total force is also equal to mass times acceleration. So that means that the weight of the 4 kilogram object minus the tension is equal to mass times acceleration. Now the weight of the 4 kilogram object is given by mg, which is equal to mass 4 times gravity, 9.81. So multiplying these two together, you get 39.24 newtons. That's the weight of the 4 kilogram object. Plugging this information in here, we get 39.24 minus the tension is equal to the mass 4 times the acceleration, which is as yet unknown. Now, what I'm going to do is I'm going to move the tension to the other side and move the 4a to the first side. So that's going to give us 39.24 minus 4A is equal to the tension. So we're going to start with this equation, and that is as far as we can get just examining the 4 kilogram object. Now let's take a look at the 2 kilogram object. In the x direction, the total force is going to be given by the tension minus weight sine 40 degrees. So, since total force is equal to mass times acceleration, that means, and this is the weight of the 2 kilogram object, that means that when I put these together, tension minus weight 2 sine 40 degrees is equal to mass times acceleration. Now, the weight of the 2 kilogram object is given by mg. The mass is 2, gravity is 9.81, so that means that the weight is equal to 19.62 newtons. So that means that tension minus 19.62 sine 40 degrees is equal to the mass, 2, times the acceleration. Now, 19.62 sine 40 degrees is 12.61. So tension minus 12.61 is equal to 2 times acceleration. So this is as far as we can get using this free body diagram for the 2 kilogram object. So to sum up, in the free body diagram for the 4 kilogram object, we worked out that 39.24 minus 4A is equal to the tension. And for the 2 kilogram object, we worked out that tension minus 12.61 gives us 2A. Now it's just a case of substituting for tension in both of these equations, and we can solve for the acceleration. So 39.24 minus 4A minus 12.61 is equal to 2A. Let's move the 4A over to the other side, and then let's do this subtraction. So 39.24 minus 12.61, that's going to be 3, 6, 8, 28.63. And I'll add the 4A to the other side to give me 6A. So the acceleration is going to become, actually just to be on the safe side, 39.24 minus 12.61 is 26.63. Yeah, it's got to be careful about that sort of thing. 26.63 divided by 6 gives us 4.43. Or 4.44, I suppose, if we round it. And this would be in meters per second squared, since it's an acceleration. So this is the acceleration for both of these objects. Remember, they have to have the same acceleration, because if they didn't, then the string would either bunch up or snap. So the 4 kilogram object has an acceleration of 4.44 j hat, and the 2 kilogram object has an acceleration of 4.44 I hat. Now, the last thing to solve for is the tension. And we were told that we could use either one of these equations to solve for it. I think the second one looks a little easier. So, tension minus 12.61 equals 2 times 4.44. Therefore, 2 times 4.44 plus 12.61 gives us 21.49. So the tension in this rope, or in this string, is 21.49 newtons.